Welcome to the lecture series on deep learning in artificial neural networks. This video covers the first element of convolutional neural networks, and that is the convolutional filters. So what are convolutional filters? Here is my image, and instead of looking at this 28 times 28 pixel image, I just look at a 5 times 5 image. Now, in this image, I apply a filter. The filter here is 3 times 3. And for the sake of simplicity, I assume that both the filter and the image are binary. They have just values of 0 or 1. And so I take this filter and put it at the first position. And then I multiply out. I take the first element of the image and multiply it with the first element of the filter. And then I do the same, second element of the image, second element of the filter. And this way I run through, I add them up, and this gives my first entry, the number 4. So this is the entry at location 1, 1. And what I do here is I sum over all x over all y of that filter wxy. That's my 3 times 3 filter in this case. And I start for 1, 1. I take the index I equal 1, j equal 1. I start with x equal 1 minus 1. So it's the same location. That was this part, then this part, that part, until we covered all these 9.9 elements. And this gives the first element. And now we calculate the same way the other elements A21, A31, A32, A33. And so this is now the final element A33. And you can check again that this is exactly evaluating the filter applied to this patch of the image. And this is now how it looks in practice. I have a real image. I shift the first filter across, I shift the second filter across. The second filter is detecting edges that are slightly diagonal. It gives this upper image here. The other image, the other feature map was created with slightly different filter. Now you can imagine that I have filters with different orientations. And so I have not just one of these filters, I have multiple filters that give rise to multiple features. Each feature is a full map, and this gives the notion of a feature map. Now, that was black and white. It's slightly more complicated because we have 3 color channels. So this is the channel 0, this is the channel 1, this is the channel 2. And again, I have filters that are 3 times 3. But I apply one filter in the color channel 0, the second filter in the color channel 1, the third filter in the color channel 2. So in total, I have 3 times 3 plus 3 times 3 plus 3 times 3. So I have 3 times 3 times 3. That's the filter. And that's now just one of the filters. That was my filter W1, but I could have a second filter giving rise to a second feature map and further filters. One more thing I would like to explain with that image is padding. On the previous slide, I had a 5.5 image. Now, this was the 5.5 image, but now we just extended it to 7 times 7 by adding zeros at the borders. And this allows us to place the center of the filter, the center of this 3 times 3 filter at the border of the image, which is convenient for some applications. And so now these are my 3 color channels. This is my filter, and now I do the same convolution as before. And here you see the first filter applied, and the entries go into this matrix. Then we go to the second filter, and the entries go in the second feature map And if we have 10 filters, then 10 different feature maps would be created. So here you see again the application of the first filter giving rise to the first filter map, then the application of the second filter giving rise to the second feature map. One thing you should notice is that the filter always is applied at steps of 2. It goes here and then there and then to the final position. So this movement by 2 steps at a time is called stride 2 and is convenient to compress the final number of outputs that we have in the feature map. So my image has now 3 values, X, Y, and C. C is the color channel, that's like the depth of the image. And then I have my X and Y direction, and suppose it's 32 times 32. So in total, I have 32 times 3 real values. Now, one of my filters in this example has 5 times 5 times 3. So it's now filters that are a little bit larger spatially, and they cover the 3 color channels. And then I can place this filter at all possible locations, and the results give rise to this first feature map here. Now, this first filter could look like this, and then I would have a second filter and a third filter, and the second filter may look like this, and in total I have here 10 filters. So the volume, the thickness gives here 10 filters, and then I have these numbers 32 times 32. How does this come about? Well, the filter is 5.5. If I want to place it at the borders, then I need a padding of 2. So I have 2 rows of extra zeros so that I can place the center of the filter at the border. And then what I can do is I shift it step by step, which is called 1 step at a time, stride 1. Now the formula is the same, I, J, K, same as before. The new thing is that I sum also the results over the different color channels. The filter has this thickness of 3 that corresponds to the 3 color channels, and I sum over these 3 color channels in addition to all the X locations and all the Y locations of the filter. So what we just saw was a padding of 2 rows of zeros around the image, stride 1. I move 1 step at a time, and 10 filters as indicated here. Then we get the volume of 32 times 32 times 10. Now with padding 0 and stride 2, that means I move the filter 2 steps at a time, then we will get a smaller volume, 14 times 10. With padding 0, stride 1, we will get a smaller volume, 28 times 10. So take a minute, redo the calculations. Are these calculations correct? Just try it out. And the answer is yes and yes. Now, let's look at this second case, padding 0, stride 2. The claim is the filter will be placed in all borders. Is this correct? Well, no, this is not correct, because if you do the count, you see that you will, if you start in the upper left-hand corner, you will see that you don't end up with the last placement in the lower right-hand corner. The reason is this stride 2 steps at a time. Last question, the volume is proportional to the number of filters. And yes, this is the case. The volume is if I have not 10 filters but 20 filters, then the volume here would be just twice as big. So how do we compute these volumes? So how many elements do we have after this processing step? Well, suppose my image is n times n with c color channels, and I have filter of size f times f with the same number c of color channels. I work with a step size or stride of element s, and I pad p elements, 1 or 2 typically, around the image. Then this is the volume. This formula is correct if you don't have a fraction here. If you have a fraction, you would go to the integer just below, the closest integer below. And if you have a fraction, this is also an indication that corners are not reached. That's something you may want to avoid. So I started off by saying, well, there's an inductive bias of this convolutional layer. What is this inductive bias? Well, it's something like independence to translation. Let me formulate this loosely in words. A feature detector, so the shape of a filter, be it sort of this cross shape or this pink versus yellow that we saw as examples, a feature detector that's useful in one part of the image is probably also useful in another part of the image. So once you know that a vertical edge detector is good, you can use it everywhere. And this is implemented by this convolution. And the second aspect that I would also like to highlight, it's really the assumption that local features are useful. For the first few processing steps, you don't need to look at the image as a whole. It's enough to look at local features. A little note. Now, a convolutional layer is in some sense just a special case of the normal dense connectivity from one layer to the next. It's a special case such that many neurons have the same weights, and that gives exactly the point 1 above. This gives this independence to translation. This gives the fact that the feature detector is the same at every point in the image. And the other thing, many weights are effectively 0 if you compare with a full network, except in a small neighborhood, and this is the point 2, this is the local features. Now, let me just try to illustrate these points in the following slides. This is the image of a cow, and I have a dense connectivity, which means every neuron, like this neuron 8, looks at the full image. It gets input connections from every pixel of the image. Same for neuron number 2. Now let's change this and say neuron number 8 only gets input from one segment of the image and neuron number 2 from another segment of the image. And now we can continue like this and say neuron number 5 also gets segments from an image, but it has different weights. So neuron number 8 and neuron number 2 would use the same filter, the filter with index 1, WXY1, whereas neuron number 7 and number 5 would use a different filter. Now, the fact that neuron number 2 and 8 use the same filter, people also say they share the weights. That actually means it's as if neuron number 2 would see all segments of the image. It would not just see its natural lower left part of the image, but also the upper right corner and so forth. So in that sense, weight sharing is very similar to data augmentation, where I just say I know that when I want to learn feature detectors, it doesn't matter where on the image the feature is. I can use all segments of the image to train up the filter of one of these neurons. So a convolutional layer is a special case of a dense layer where many neurons share the same weights, and many weights are zero, except in a small neighborhood. So a normal deep network also has a solution. It could find a solution where many neurons have the same weights. It could find a solution where many weights are zero, except in a small neighborhood. But a convolutional network imposes this in the form of a prior choice, in the form of an inductive bias. And so this convolutional layer brings two intuitions in the form of the inductive bias: the independence to translation of the filter. In other words, a feature detector that's useful in one part of the image should also be useful in another part of the image, and we impose this by this weight sharing. And the second intuition or inductive bias is local features are useful elements to understand images.